This is a video recording for our lower secondary science physics chapter 1 on units and measurement. At any point in time, you may choose to pause the video, scribble down your notes, or you may choose to rewind and play certain parts again if you did not manage to capture what was mentioned on the video. Now, let's talk about measurements in the past. Many years ago, we didn't have units such as meters, inches, kilograms, seconds, etc. So how do you think people in the past compared quantities? For example, if you are selling cloth, how would you charge your customers? Because in the past, you couldn't say, oh, I'm going to charge you 1 square meters for $10 and so on and so forth, because they didn't have such units. So in the past, people tried to measure using their body parts, for example their feet. So that is how we have one of the units called feet as a measurement of length today. So suppose in the past you decided to sell cloth at $3 per foot, and then you have these two employees who are here to try and sell cloth for you. Who will you employ? So this person A, has small feet, whereas person B has large feet. So you're trying to sell cloth, right? You want to make the most money. Who will you employ? If I am the person selling, I will employ person A to sell my cloth, because for the same $3, I am only going to part with a small piece of cloth, so I can earn more. However, if you are a customer buying cloth and both these people are selling at $3 per foot and they're using the feet size to measure, who will you buy the cloth from? Now, as a customer, it would make sense to buy from person B, because for the same $3 you get much more. But is this a good way of measuring? So we need to ensure that it is fair and consistent. So we need to standardize the way we measure quantities, which is why it is important in physics. The way we measure must be fair and standardized. So for measurement is an important process of science. Theories. We can only be sure our theories are correct if we conduct experiments, and we must make measurements to verify that our theories predicted the outcomes of the experiments correctly. Can you imagine if you come up with a theory and then you conduct the experiment, but the measurements are not taken well? You will never be able to prove whether your theories are right or wrong, because nobody can trust your readings. Okay, so only by making accurate measurements then can we be sure our theories are correct. Okay, so what exactly do we measure? There are many things that we can measure, and they are known as physical quantities. So physical quantities, they describe physical properties of objects by measurements, and these physical quantities, they consist of two parts. First is the magnitude, otherwise known as the amount, or if you like, is the size. Next will be something I'm more familiar with, the units. What are we using to measure? Are they measured in kilograms, grams, so on and so forth? Okay, so along the way in the slides, there will be some blanks for you which you have to fill up. So for example, I give it a description. A seedling, a plant, is 0.10 meters tall. So what is the physical quantity that we are measuring? Something is 0.10 meters tall, we are measuring the length. So write this down, we are measuring the length. That is the physical quantity. What is the magnitude? What is the size of this measurement? The size is 0.10, and we still require the unit. In this case, the unit is meter, and we can use this abbreviation M for meter. I'm sure you've been using that since primary school. So the next description, the mass of fertilizer is 0.05 kilograms. The physical quantity that we are measuring in this case will be the mass. Many people are confused over the difference between mass and weight, which is something that we will explore in physics in subsequent lessons. But for now, you can treat mass as something very similar to weight for now. Okay, so the magnitude in this example is 0.05. That is the value, the size, and the unit will be kilograms in this example. Next, can a physical quantity be measured using two different units? So the answer is yes, and these are two examples. This is one example of two heights being measured, one in centimeters and the other measured in feet and inches, two different units, so it is possible. Now, we can also have quantities with magnitude but no units. So these are two examples. There is we can have a magnitude, the number of people, the head count of people. For example, 1,000 students in Evergreen Secondary. There are no units. It is just a magnitude, it's just a number. For example, the number of stones on the floor. There are 200 stones on the floor. There are no units. You cannot say there are 200 kilograms, 200 meters of stones on the floor. We only have magnitude in this case because we are counting. Next, suppose you are made to conduct an experiment, and this experiment is to find out how the amount of fertilizer used affects the growth of plant seedlings. So logically, we would think that if we use more fertilizer, then the seedlings will grow taller. So two physical quantities that we need to measure in order to conduct the experiment will firstly be the mass of fertilizer. Next will be the height of the seedlings. So the physical quantities in this case are mass and height. Mass of what? Mass of fertilizer. Height of what? Height of the seedlings. Okay, so these are some examples of physical quantities. Are there more physical quantities to mass and height or length? Definitely. Okay, so next part, base quantities and SI units. This will be a phrase that we must be very familiar with. We will keep repeating this phrase, SI units. So what does it stand for? The International System of Units. In short, this is called SI. So throughout physics, we will keep hearing us repeat again and again, SI units, SI units. So there are 7 units of measure as a basic set of units, otherwise known as base units. What are these 7 units of measure? So we'll explore that in a while. Now, base quantities, they are fundamental physical quantities which all other physical quantities can be written in terms of. In other words, all physical quantities are made of a combination of the base quantities. And earlier we mentioned that there are 7 of them. And these 7, when combined together, gives us other physical quantities. So what are these special 7 base quantities? They are our length, so the SI unit will be meter, in short just a simple M. We have mass, which I've mentioned is similar to weight, but they are not the same in physics. So we use kilograms as a unit, as the SI unit for mass. For time, the SI unit is not minutes, it's not hours, it is seconds, and so on and so forth. Okay, so do we need to know this? Yes, we need to memorize this. Okay, it is very important that you memorize everything, including the spelling, because we are going to be building everything on these 7 base quantities, 7 of them. Okay, so these are the fundamental building blocks for us to create other quantities to measure physical properties. How do we combine these to give us something else? Okay, something that you should be familiar with. What can we obtain from, for example, meters and seconds? A distance, a length, and time. Does speed come to mind? How do we get speed? We learned it in primary school. Distance divided by time. And the units will be meters per second in this case. So what we have just done is to combine meters and seconds together to create a new quantity called speed, and its units will be meters per second. So that is just one example. There are many examples in physics. Okay, so these are examples of the base quantities and the derived quantities. Okay, so as mentioned, speed. Speed is a derived quantity. It is not one of the 7. So derived quantity, not one of the 7 base quantity. Okay, as long as it's not one of the 7 base quantities, it must be derived. So we have speed. The units for speed, meters per second. The base units, we have meters over here, and we have seconds. So where did this speed come from? It came from the base quantities of length and time, right? So the unit for length, meters. The unit for time, seconds. And we are only talking about SI units. So in this table, there are 3 other examples which you will be covering in future. Just know for now that everything else must be made up of the 7 base quantities. All these, everything found over here, they are one of the 7. One of the 7 base quantities over here. Okay, next. We need to know this term prefix, okay? Prefixes are added to SI units to obtain a larger or smaller unit. So some of the common prefixes used, you are familiar with some of them already. For example, kilo. A prefix comes before an SI unit. So for example, we've got kilometer. That will be 1000 meters. Kilogram, that will be 1000 grams. So when you see the letter K like this, it implies it is 1000. Besides kilo, we are also familiar with things like milli, okay, with a little m. So we've got, for example, millisecond. That refers to 1000th. So 1 over 1000 of a second. So 1 millisecond is actually 1 over 1000 second. It is a very small amount of time. You're also familiar with 1 millimeter, which is the same as 1 over 1000 meter. Okay, so then we have other things such as centi, which is 1 over 100. We also have micro, which is 1 over 1 million with 6 zeros. Is this slide important? Yes, memorize. Next, we have the measurement of length. Now, everybody can measure length. Everybody knows how to measure. But in physics, we will learn how to measure different things with different instruments. The most basic and the most common instrument that we use in physics will be our meter rule. It is not a typo, it is not a meter ruler, but you can think of, but it is literally a ruler that is 1 meter long. Okay, we call it a meter rule. This meter rule is usually made of wood. So this over here is a portion of a meter rule shown. Meter rules are similar to the rulers you have in your pencil cases. So if you have one, you may take it out and look at it. What is the smallest division that you can see on your ruler? Remember, it's very similar to our meter rule. The smallest spacing over here, for example, 1 millimeter. It allows us to read or to measure up to 1 millimeter, which is the same as 0.1 centimeter. Okay, so if you were told to measure your eraser, for example, possible readings from your ruler and from this meter rule could be 23 millimeters. It could be 28 millimeters, for example. Is it possible for us to read 23.2 millimeters on our rulers? No, we can't, because the smallest division is only 1 millimeter. You can't go smaller than that. And we call this the precision of the ruler. This ruler only allows us to measure with a precision of 1 millimeter, otherwise known as 0.1 centimeters. We can't go smaller than 1 millimeter. Okay? Okay, next. Here we have the meter rule. It's 1 meter. When we measure, there are two ways we can do it. This is the first way. Sorry. Okay. This is the first way, and this is the second way. In the first method, we place our eyes perpendicular to the ruler. Okay, we look perpendicularly at the ruler. So this eye actually reads 1 cm. Okay, this eye says 1 cm, and this eye actually reads 2.9 cm. Whereas in the second case, this eye, if you follow the dotted line, it reads 1.1 cm, and on this side it reads 2.7 cm. Which do you think is more accurate? Number 1 is more accurate. Number 2 is an inaccurate reading. So we have a term to describe this. If you are reading it correctly like this, eyes perpendicular to the ruler, we say that there is no parallax error. No parallax error. Whereas if you read like number 2 over here, we say that there is a parallax error. So this is an error, we have to avoid it. So now you know how to take readings from your meter rule or from your own ruler. Okay, we want this case. We do not like this case. So measurement of length. So this is our object. Okay. Let me put it back. So this is our object, and if we are told to measure the length, we will read. Okay, the larger reading is 30.7. Take note that the precision of this ruler is 1 mm or 0.1 cm. So we can only allow one decimal place if we are using centimeters. So 30.7. You cannot say 30.71 or it looks a bit less than 30.7, it is 30.68. You can't do that. It is 30.7 centimeters. And the smaller reading is 23. Exactly right? Exactly 23. But because the precision is 0.1 cm, we're going to include the 0.0. So you subtract them and we get the length of 7.7 centimeters. This one decimal place implies, it tells us that the precision of the instrument we are using, the precision is 0.1 centimeter. So as shown over here, this is a meter rule. The precision, the smallest gap will be 0.1 centimeters, which is the same as 1 millimeter. Okay, so I've mentioned this word a few times, the precision. It is reflected in the decimal places of the units used. So for example, I've got two readings over here. First reading 4.0 centimeters, second reading 4.000 centimeters. Which one of these readings came from a meter rule? So recap, meter rule only allows us to read up to 0.1 centimeters. So your readings can only be, for example, 3.9 cm, 3.6 cm. You cannot have two decimal places if you are using centimeters for a meter rule, because you can't get smaller than that. So the answer should be clear now. 4.0 centimeters. This reading was taken from, this reading over here was taken from a meter rule. Hey, then what about this reading over here? 4.000 centimeters. It is very precise. You are saying to me that, oh, I have measured this object and the length is 4.000 centimeters exactly. Okay, compared to using a meter rule. Meter rule just says it is 4.0 centimeters. Maybe a little bit more, maybe a little bit less. I can't really tell because my ruler is not precise enough. Whereas in the second case, we say with confidence it is 4.000 centimeters. Very precise. So another instrument was used. Okay. So besides using a ruler to measure, we have this object, this tool, this instrument known as the vernier calipers. Must know how to spell. Okay, now we've got a few parts of this vernier calipers. I'll use an example of a test tube. Okay, so this is the cross section of a test tube made of glass. Got the inside, there's the outside, and there's a depth. So the outside jaws of the vernier calipers, these are the outside jaws over here. They are called jaws because they open and close like a mouth. So these jaws are used to take external measures of objects. So I can use my vernier calipers and I place it over here. Okay, so I clamp it shut and I take the measurement of the external diameter of the test tube. Then I can also use the inner jaws, the inside jaws, to measure the internal measures, the internal diameter of this test tube. So I stick this portion inside and measure. Okay, so yeah, very bad drawing, but you get the idea. You measure the inside diameter with these vernier calipers. And we've got one last part. This is the third part. It's called the depth probe. So this portion can extend. Okay, and it goes, we place it inside here in order to measure how deep it is. The next two And the final two that we're going to talk about, they are very important. Okay, the main scale, which is measured in centimeters. So the main scale looks like a ruler. Okay, you've got 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, so on and so forth, centimeters. That is our main scale. Then we have this part number 6, known as the vernier scale. Okay, this portion is the vernier scale. Okay, I'll explain a little more. But first, let's talk about the precision of a vernier calipers. The precision of the vernier calipers is 0.1 millimeter, or it is the same as 0.01 centimeter. Recall that the precision of a meter rule, it has a precision of 1 millimeter. This is our meter rule. The smallest gap is 1 millimeter. And how precise is our vernier calipers now? It is actually 0.1 millimeter. In other words, we've got markings more fine, more precise than the meter rule by 10 times. Okay, so you cannot use your meter rule, for example, to measure human hair, the diameter of a human hair. Suppose you got a human hair, you place it over here. Okay, let me use a black color for the human hair. Suppose I got a human hair like this. How do you measure the thickness of this human hair? It is smaller than 1 millimeter. So can you say that it is 0.1 millimeter? Can you say it is 0.2 millimeters using our meter rule? You can't, because it is not precise enough. The gap, the spacing between two lines is 1 millimeter, which is not small enough. So we can use our vernier calipers, which is more precise. It allows us to read up to 2 decimal places for centimeters. So we can use our vernier calipers to measure the diameter of this hair. Okay, so a comparison of the vernier calipers and the meter rule. This slide, important, memorize. In fact, you don't really need to memorize for the meter ruler because it's the same as a ruler. You can easily take it out, look at the smallest gap, that is 1 millimeter, and that's it. Vernier calipers, divide it by 10 because it is more powerful. So it's not difficult to memorize this. Now, how does a vernier calipers work? This vernier calipers has a jaw, right? It has these jaws that can open and close. Okay, so just give me a moment. Okay, so it opens this way for us to measure. Okay, next. These were mentioned before. You can go to this link to watch a video on the usage of a vernier calipers. So of course, now we have to learn how to read using vernier calipers. So for example, vernier calipers can be used to measure the diameter of this ball bearing. Okay, first, step 1, we grip using the outside jaws, grip the ball bearing. Then step 2, we look at this portion over here. Okay, this portion, we zoom in, this is what we will see. Remember, there's a main scale which is in centimeters, which is like our ruler. Then we have the vernier scale at the bottom, which slides. We need to first find on the vernier scale where the 0 is. Okay, so the 0 is over here on the vernier scale. Once we have identified it, you look back at the main scale. What is the marking just before the 0? The marking just before the 0 is this, right? It is just before the 0 over here. and tell me what is this value. This value is 3.1. Okay, so this is what I'll do. Reading equals to 3.1, but we are not done yet. 3.1. The next step, we have to compare the vernier scale with the main scale. There are so many lines, right? So many divisions. There will only be one division, there will only be one line on the main scale which coincides with one line on the vernier scale. That means they form one perfect vertical line. Can you find where that is? So let's take a look at this one. Does it form a perfect straight line with any of the markings on the main scale? No, it doesn't. Let's move on to the next one. It doesn't form a perfect straight line, vertical line with the main scale. This neither does this. But we see over here, hey, these two, they form a perfect line, and this is what I'm interested in. Everything else is not a line. See, they're all they're not forming one perfect line. So this is what I'm interested in. Now I go back to my vernier scale and I try and find out what this value is. So this being 0, this being 10, this must be 1, 2, 3, 4. Okay, this must be 4. And I just put the 4 over here, cm. Done. This is my reading. If you were to use a ruler to measure the diameter of the sphere, it is going to be very difficult. Not just that, you will only be able to get probably a reading of 3.1 cm. You cannot get a 4 because a ruler is precise only up to 0.1 centimeters. So let's have more examples. Reading of vernier calipers. So first step, we find on the vernier scale, this is our vernier, this is our vernier scale. Well, this is our main scale. So as mentioned, we go to our vernier scale, find the 0. Okay, this is my 0. Then look at the main scale, the marking just before the 0. That will be this one. Okay, this is the marking on the main scale just before the 0. So we are ready to write down reading equals to the reading just before the 0 will be 0.1, 0.2, 0.3. Write down 0.3. We are not done yet. Now we go and look for the line that coincides. Okay, this is the one that coincides both the main scale and the vernier scale. So this 0, this 10, this is 1, 2, 3, 4, 5, 6. 0.36 centimeters. Okay, so this is how I do it. You may choose to do it this way. You do not have to show the working. You can do it the way I did it. Okay, so next, more examples. So over here, we've got our vernier scale and our main scale. So we are ready right now. Reading, okay, equals to, take note where the 0 is on the vernier scale. Okay, it is over here. Look at the main scale just before it. So we've got a reading of 1.1, 1.2. So right now reading is 1.2. We are not done yet. Find the marking that coincides. Okay, this is the one that coincides. Everything else is to the left or to the right of the main scale. So this being 0, this being 10, this must be 1, and this must be 2. So the reading is 1.22 cm. So you can go to this website to try using a virtual vernier calipers, and you can test your understanding of how to read a vernier calipers. Okay. Next, Have you seen, okay, this is a weighing machine, a weighing scale. Is there a problem with it? Do you see a problem with it? When there is nothing placed, where should the needle point? The needle should be pointing at 0, isn't it? But now it is pointing to the left of 0. So what happens if I place something very light on it? So if I place something, then the scale will move, right? In fact, after I place something, the scale may tell me, oh, 0 kilograms. But can that be possible? It can't be possible. I can't place something on a weighing machine and the machine tells me, oh, the weight over here, 0 kilograms. Then we should understand that, hey, there's an error over there. This error is known as a zero error. Okay, so in our notes, zero error is an indication that the measuring system gives a false reading. Means it gives you something that is wrong when the true value is supposed to be 0. Meaning, when it is supposed to be 0, it tells you something else. It either tells you 1 kilogram when it is 0 kilogram, or it tells you negative 1 kilogram when it is supposed to be 0 kilograms. So that is an example for kilograms. That will be for mass. But what about for vernier calipers? Yes, we can have 0 errors in vernier calipers. But let's talk about the example when our vernier calipers doesn't have anything wrong. It is perfect. So if there is no 0 error, means it is working well. Then when we close it, when we close the jaws, it means we are not measuring anything, right? If we are not measuring anything, then the reading should be 0. That means there is no 0 error. So when we close them up, we should see that the 0 on the main scale must be together with the 0 on the vernier scale. When they meet each other, then we know that our vernier calipers does not have a problem. It doesn't have any 0 errors. Okay, so there are subsequently I will show you other 0 errors in vernier calipers. Okay, so as the title suggests over here, positive 0 errors. If I have 0 errors that are positive, it implies that there will be 0 errors that are negative. But let's for now talk about positive 0 errors, which means when my vernier calipers, they are closed, right? When they are closed, the 0 and the 0, they are supposed to meet each other. But in this case, they did not meet each other. In fact, my vernier scale is slightly to the right of the main scale. How much is it to the right? Okay, so we can read this reading over here, and we'll see that okay, this is 0.0123. This vernier calipers tells me, hey, your reading is 0.03 centimeters when you have nothing measured. That tells me something is wrong, right? When there is nothing placed there, it tells me a reading, not 0, but it's telling me, you know, the size of this nothing over here is 0.03 centimeters. So if I know that there is such a problem, and I use these vernier calipers to measure something, for example, I use it to measure my eraser. Okay, I use this faulty one to measure my eraser, and it says, okay, let's see what this says now. Reading will be 3. Find the 0 over here. Okay, this is what I'm interested in. This is 3.1. Then I find where it coincides. Okay, it coincides here, which is 3.17 centimeters. My reading is 3.17 centimeters. Is this reading the correct reading? Is it the true length of my eraser? keeping in mind that when I was measuring nothing, it already gave me an extra 0.03 centimeters. So in order to get a correct reading, I must remove this extra 0.03, isn't it? So that's where we have the corrected reading. We take what we saw, 3.17, we subtract, we minus away, okay, we subtract the error, which is 0.03, to get 3.14 centimeters. Okay, so this is our corrected reading. Recap, summary, positive zero error. It is giving me extra reading. How much extra? 0.03 centimeters in this case. So everything that I read, I must remove, I must subtract this extra 0.03 centimeters to get the actual reading. So as mentioned, there are positive zero errors, there must be negative zero errors. So this time, when my vernier calipers is not measuring anything, okay, they are closed, the opposite happens. Instead of giving me extra length, it is now giving me negative length. Okay, so we look over here, our vernier scale is now to the left of the main scale. Look at the zero over here, it is on the left of the zero of the main scale. By right, the zeros should be aligned, should be one straight line. But now, the zero on the vernier scale is to the left, which tells us that there is a negative zero error. Before I started measuring, it's already telling me, oh, you don't have enough. You don't have enough. You are unable to measure correctly already. Okay, so it's the opposite problem of positive zero error. So how much is the negative zero error? This time, being a negative error, we will count from the back. Okay, so from the 10, count 1, division, 2 and 3 where they coincide. So that will be negative 0.03 centimeters. So if again I want to measure my eraser, same eraser as the previous one, I measure and read. Okay, it says 3.11. This is what I get from my vernier calipers, 3.11 centimeters. But at the back of my mind, I know that there is an error already. It is owing me. It owes me 0.03 centimeters. Right, before I even measure anything, it's already saying, oh, you got negative reading. So what should I do? This time, I will add the 0.03 to it to get 3.14 centimeters. Now you can think of it this way. When you have a positive zero error of 0.03, you just take 3.17 minus 0.03 to get the correct answer. When you have a negative zero error, in this case negative 0.03, then to get a corrected value, you must add it back. So 3.11 plus 0.03 to get 3.14. Or alternatively, you can use mathematics over here. We are always subtracting the negative error. So 3.11 subtract. We minus away the negative 0.03. You will learn soon in mathematics that when you have, for example, 5 minus negative 2, it is actually the same as 5 plus 2, which is 7. So similarly over here, we have 3.11 plus 0.03 to get 3.14 cm. Okay? Now next, what are the zero errors for these vernier calipers? So for this particular one, we see that the vernier scale is to the right. See this 0 is slightly to the right of this 0. So we know there's a positive zero error. How much is the positive error? We have to find where they coincide. where do they have a vertical continuous straight line? So it's over here. This is where we have a match. So this reading will therefore be 0.01 centimeters. Okay, so the answer, positive 0.01 cm. Next, now this vernier scale, we can see that it is slightly to the left. Okay, this 0 is to the left of the 0 on the main scale. So we conclude, okay, there is a negative 0 error. Then since it is a negative 0 error, we count from the back. So here, until we find where the lines coincide. So from here, doesn't coincide. Over here it coincides. So we have 1 and 2. So the answer will be a negative 0.02 centimeters for the 0 error. It is a negative 0 error. Okay, next, determine the length of the object. So this is the vernier calipers that is used. On the left, it is when it is closed, when it is shut. When it is shut, can we see that this 0 for this vernier scale is slightly to the left of the 0 on the main scale? So I know that there must be a negative 0 error. So for negative 0 errors, we start counting from the back. Okay, so for negative 0 errors, we start counting from back. Okay, this is where they coincide, that is 0.01 centimeters. So my 0 error is negative 0.01 cm. Keeping this in mind, we go to our measurement on the right. So this is our object. Then we measure, we find the 0 on the vernier scale, you find the reading just before it. So this is actually 1.1. We find where it coincides. Okay, it coincides over here. So the reading is 1.14 cm. The observed reading, what I see first, I see it is 1.14 centimeters. Then I have to correct it because I know there was a 0 error. There was a negative 0.01 centimeter error. So we will always take the observed reading minus the error. 1.14 minus the error of negative 0.01. So these two negative, they combine to become a positive. Therefore, the correct reading is 1.15 centimeters. Okay, so practice yourself. Access this website. Okay, it is a simulator for the vernier calipers. You may use your QR code to get to the website. Set yourself 3 arbitrary lengths to measure using the virtual vernier calipers. This is going to help you understand how to use it, and it is going to be useful for your tests and examinations. After you have done that, test your friend. Okay, choose 2 readings, one with a positive 0 error, one with a negative 0 error. Okay, next one. We've got measurements of length with our vernier calipers. Let's talk about the measurement of time. Okay, so for measuring time, we use a digital stopwatch. We hardly use the analog stopwatches anymore. We use this kind. How do we read a digital stopwatch? I'm sure many of you know. You can practice it during your PE. So the first few digits will be the minutes, then there will be a blank space, followed by the seconds, followed by the 100th of a second. Okay, so in this case, it reads, it may not be very clear, but this is 9 and 9. So this is 0.99 of a second. So from this stopwatch, we can see that the reading is 19.99 seconds. And the precision, look at the number of decimal places. We've got 2 decimal places over here, therefore the precision must be like this, with 2 decimal places and the last, all digits are 0, last digit is 1. So the precision is 0.01 seconds. Is that very precise? Yes, it is very precise. No, it is. These are examples of hand-operated stopwatches. There's a problem. They may be very precise, but the person using it is not very accurate. Because, for example, you run round the school field 1 round, and your friend is supposed to time you. By the time you finish 1 round, your friend should stop the stopwatch for an accurate reading. But just as you cross the finishing line, your friend's eyes, he sees that you have crossed it, but it takes a short amount of time for his eyes to tell his brain that you have crossed the finishing line, and then it takes a little bit of time for your brain to tell your fingers to press the button. So there's this very short delay. It is known as the human reaction time error. Okay, so this phrase, important, memorize it. So all of us, we have reaction time. If you can react very quickly, good for you. So how do we test whether we can react fast or not? So this is a simple game you can play with your friend. So for example, you hold a ruler, you be the one, this is you, and this is your friend. The objective is for you to suddenly release the ruler and see if your friend can catch it. If your friend can catch it, then his reaction is really fast. Okay? Now next, this is a phrase that we need to be familiar with as well, called periodic motion. So some objects, okay, in this we call it bodies. Okay, we can just take it as some objects. Some objects in nature, they repeat itself continuously in endless oscillations. So this repetitive motion is called periodic motion. For example, a child on a swing. So he swings from the side view, from the left, then he swings to the right, then he swings back to the left, then he swings back to the right. This is periodic. It repeats itself. Sometimes in the ocean, you see buoys. Okay, so something like this floating in the ocean. It is bobbing up and down, up and down, up and down. So this is repetitive motion in endless oscillations, also known as periodic motion. And the vibrating engine, for example in a bus, you can feel the engine vibrating. It repeats itself continuously. That's periodic motion. In our classroom, if you look up, the ceiling fan, it is going round and round, periodic motion again. If you look at the wall fan, it is swinging from left to right, to left to right to left. That is also periodic motion. So next, we have this phrase known as the period. It is defined as the time needed for a body to complete one oscillation. Okay, so go to this website to observe the oscillations of a pendulum. So pendulums, basically just a string with a bob at the bottom. So it swings back and forth. Okay. So another website for you to self-explore. So this is a simple pendulum that we can have in our lab. So you have a bob, it's tied to a string, and we move it to the side and we release it. So from A it goes to B, B goes to C, C goes back to B, B goes back to A, and it repeats itself over and over again. So what exactly is a complete oscillation? For example, if you were to, so as the pendulum is swinging left, right, left, right, left, right, left, right, you watch closely. When it goes to A, you start your stopwatch. Okay, that is the start of our oscillation. Then it goes to B, goes to C. Is that complete? No, it's not complete. It has to go back to B, it has to go back to A, then that is one complete oscillation. So what I have just described will be this case. One complete oscillation. The time taken will be known as the period. Alternatively, as the bob is swinging A to B to C, to B to A, to B to C, swinging and swinging, then as it goes back to B, you can choose to start recording. You can choose to start timing when it reaches B. Then once it's at B, it goes to C, then it goes back to B. Is that a complete oscillation? Not yet. It has to go to A again, then back to B. Now that is one complete oscillation, which is what I've just described over here. And if you compare the time between what we have at the top and what we have at the bottom for one oscillation, you will find that they are the same. So please copy this down. The period of a pendulum is the time taken, there's an N over here, for one complete oscillation. You need to memorize this. It is not difficult, it's just the time taken for one complete oscillation. Okay, so we want to find the period of a pendulum. Just now I mentioned that you can use a stopwatch and time, right? You can use a stopwatch and time from A to B to C, back to B, back to A. But is it a good idea? The time taken for one oscillation is short, and we recall that we all have errors in our timing, right? Known as the human reaction time error. So for one oscillation which takes a short while, can you imagine that you have human reaction time error when you start and when you stop? So your reading is not going to be accurate. Then what should we do? Okay, so watch this video to see how you can conduct a pendulum experiment. So in this case, the person took the time, recorded the time taken for 20 oscillations. So for 20 oscillations, it took the person 33.3 seconds. So the time taken for one oscillation, otherwise known as the period, is 33.3 divided by 20 to get 1.67 seconds. Why 1.67? If you were to use your calculator, you will see a different value, 1.665 if I'm not wrong, but it is rounded off. It is rounded off to, watch this, 3 significant figures, 3 SF. You will learn this in maths. Okay, for now, don't need to be too bothered about it. Your maths teacher will teach you about significant figures. So why take 20 oscillations? It's because we want to improve the accuracy of the experiment. Okay, we take the time for 20 oscillations instead of just one. Then we obtain the period by dividing the time recorded by 20. That is because we've got human reaction time at the start and at the end. So by taking the total time for 20 oscillations and then we divide the total time by 20 in order to get a time for one oscillation, we are also dividing our human reaction time by 20. Does that make sense? We are spreading out the human reaction time over 20 oscillations. So when you divide by 20, the error becomes smaller. So that is the advantage of taking an average. In addition, when we want to improve the reliability of the experiment, we should do it a few more times. I'm sure you learned it in primary school. Then the average reading is calculated. Because when more readings are taken, random errors can be reduced or it could be evened out. For example, during my first experiment, suddenly there's a wind blowing, a strong wind blowing, and it affected my results. These are random errors. I cannot help it. Okay, random errors. That is why when I do the experiment one more time, 2 more times, 3 more times, without wind interfering, then when I take the average, my results will be more accurate. So these are the advantages of taking average. Okay, so there are some experiments which we have to go through for this chapter, and we'll go through them when I'm back.